Now that we have implemented our graph class in C++, we move to the following exercise: to program a method for visiting all the nodes of a graph according to the DFS algorithm, to deep first search. So let's recap how DFS works. The idea is to explore as deep as possible a branch of nodes before moving backwards. So this is an iterative solution to the problem. Actually, DFS per se, by nature, can be resolved recursively. So that is, to make a new call of the program of DFS for all the neighbors of a node that have not been visited. Instead, what I want to show you here is how we can provide an iterative solution by means being supported by a data structure, for example, a stack. And in this way, to avoid recursion. So the solution is as follows. So as a parameter, we have a node S. So this is supposed to be the root node. For example, the node 1, like in our example of before. Then we have a stack. So remember, the stack has a LIFO policy. So the last element in is the first one that goes out. Then we are going to push the root node from this into this stack. And then in this while section, we are going to ask the following. So as long as we have elements, so that is, while not the stack is empty, perform the following instructions. So we are going to pop to take out the last element inserted in the stack. So this is supposed to be the current node that we are going to visit. In line 6, we ask, have we visited this node? So whether or not we have visited this node is a Boolean value that can be stored in an array of Booleans. And so, of course, at the beginning of the algorithm, we assume that this array has been filled before with false values for all nodes, because we have not visited any node before. So we ask, have we visited node B before? So if it's false, so we have not visited, we fall here inside the if statement, and we mark it as true. We mark that we have visited this, that we have just been visited this node, that we are visiting it. And we are going to ask for all the neighbors of this current node B. For each node U in the set of neighbors of B, we ask, have we visited a neighbor of B, which is U? If we have not visited U, we are going to push it in the stack because we are going to visit it later. And this is what we do in this block of while, to visit nodes as long as the stack has some value to visit. Before showing the algorithm in C++, the program, I will quickly provide how does it work by the help of the stack to make a run as an example. So here you see at the beginning of the algorithm how we have the stack just with value 1, and we are going to visit the neighbors 2 and 5. So what we do, we take out 1, we mark it as visited, and we push in the stack the neighbors of 1, which are 2 and 5. Then we repeat the procedure. We take out 2, and we are going to push in the stack the neighbors of 2, which are 3, 6, and 4. Then we repeat the procedure. We take 3, and we ask for the neighbors, and so on and so forth. You see that for 6, when we are going to visit 6, there are no neighbors or that have not been visited before. So which are the neighbors of 6? 2 and 7. But both of them were visited before, so we cannot push them again in the stack. So this is the part in which we go back. You see that instead 4 was not visited before, so we mark it, and then we ask. The neighbors, there are neighbors of 4 that were not visited before. So all neighbors of 4 have been visited. So we need also to move back and to pop out elements from the stack. Actually, you see that we will need to pop out elements till we get to 5, which is the last element that has not been visited before. So we mark it, we take it out from the stack, we mark it as visited, and you see that now all nodes in the graph were visited. So this is the iterative solution, and now we are going to show how to program it, the method of this algorithm in C++. So this is our graph class that we presented before. I have added a couple of modifications. updates. So the first one is that we have an attribute visited false. You saw in the algorithm that we had an array. So actually that could be other variant, other solution in which we have an array of flags, or a map, also could be a map, in which the key of the map is going to be the node, and as a value we are going to receive a Boolean value, false if we have not visited the node, or true if we already visited. In this other solution, we just inserted the visited flag, false or true, as an attribute of the node. So it's the fastest way. And when the node is created, the value is switched to false automatically. The second thing that I have added is this declaration of this method that we are going to implement, the first search. So we are going to implement it in this file. So in this file we are going to implement the method of that class. And also so you see here that in the main, I already added nodes and edges according to the graph that I presented in the slides. And at the end, I am doing the call to the graph method DFS. So here we are going to implement our method. So how does it work? So you see that I am receiving as a parameter the root node number 1. Then I have a stack, as I showed in the algorithm. This stack is from the standard template library of C++. And what I do here is to a stack of nodes, as I presented here. Then what we do, we are going to push the root node of the graph, and then we are going to complete the algorithm. So while the stack is not empty, so we are going to visit nodes. So what does this mean? That we are going to ask for a current node first. So we need to take the top element, so the last element inserted in the stack, and we need to put it out to pop. So you see that in this container of STL of C++, the stack, so we need to do it in 2 instructions. So one instruction to take the last element, and the other instruction to delete it from the container. The second thing is that we are going then to ask whether we have visited, so whether the value of this flag is false or true. So if it's false, so it means that we have not visited this node before, and we are going to print its value. So give me the data. So actually this is the visit of a node. Then the second thing is to mark it as true. So to this point we already visited the node. So what's next? We then need to ask for the neighbors of this vector. So we are going to create an iterator as follows. And I will create this for statement. I will explain it soon. Okay, so I explain it. So what are we doing here? So remember that the adjacency list, it's a multimap of pairs. So it's a container of pairs. So then we are asking for all the pairs whose value is b. So the first element of the pair is b. And then we are going in this for loop, we'll ask for the destination. So for all the pairs, so we are going to move through all the pairs of this multimap whose value is b, and we are going to call, so if all those neighbors of b have not been visited or not. So we do it as follows. So here we are moving through the neighbors of B. So the question is here. If we have not visited the node, the neighbor, so this is this Boolean condition. If we have not visited the neighbor of B, this current neighbor, we are going to push it in the stack. And with this, we conclude actually our method. So we ask it, while the stack is not empty, we are going to ask for the last node, we are going to pop it, and we are going to ask if we have visited. If we have not visited, we are going to take its data, we mark it as visited, and then we ask for the neighbors. So if we have not visited a current neighbor, we are going to push it in the stack. Finally, what I wanted to do here is to print out of end of the line, because I am printing all the elements in just one line. And now we are going to compile. Then we execute. So you see that we have performed the DFS according to the scheme of moving through as deep as we can. And this actually, you can see later that this is the same way that it performed in the example that we show it in the slides. Now I wanted to finalize this talk about how then we can implement brief first search, DFS. So here, notice this point of the algorithm. What if that here and at this point of DFS, instead of taking the last element pushed, which is 3, so remember here what we are doing, we are visiting 2 and we are pushing the neighbors, which are 3, 6, and 4. But what if instead of pushing the neighbors of 2, what if instead of visiting this last neighbor of 2, which is 3, what if take the first element of the stack instead of the last one? So you see that here then we have to change the stack structure for a queue. And this is essentially BFS. So it's DFS, but now instead of taking the last element of the stack is 3. And now then we take the first element, which is 5. So then we are going to give priority to the elements which are in the same level. So instead of going as deep in a branch, we are going to ask for all the neighbors of 1. So we are going to visit all the neighbors of 1 first. So with this hands-on presentation, we finish our tutorial, and thanks a lot for your attention.